Hello everyone. Today I am going to explain about the parallel processing approach in the low power CMOS design. Okay, so in the previous discussion I have explained about the pipeline approach. Okay, in that one the area will be more occupied while designing, but to avoid that one, here we are going with another method that is nothing but parallel processing approach. Okay, so another method for trading of area for low power dissipation is to use parallelism or hardware replication. This approach could be useful, especially when the logic function to be implemented is not suitable for pipelining. Okay, so this method is used particularly whenever we cannot we cannot use this pipeline process to implement this low power digital design or low power CMOS design. So at that point, we will go with the parallel processing approach. Okay, so here we have the circuit or the block diagram of this parallel processing approach. Okay, so it consists of n logic functions and n registers. Here you have. Okay, so consider n identical processing elements, each implementing the logic function f input in parallel. So previously what we have considered here is nothing but a pipeline approach. Pipeline means what? One pipe is suppose if in general case in water pipeline is there. Okay, so in that one pipe is attached to the another pipe is attached to the next one is attached to the last one. Okay, so like that the pipeline will be constructed. Okay, so in that one what happened is first the water enter into the first pipe. After that it will move into the second pipe, and next one is third pipe. Like what we are applying the input vectors in these registers, that is the first registers. Okay, after first register it will goes with the stage one, and that output of stage one will be given to the next register array, like that. So it is like water pipeline process here, the pipelining means. So but here in this parallel processing that's not the case. Here all the inputs, suppose input one is inserted or latched into a first register, the same input will be latched into the remaining registers at the same clock. Okay, so here that is the point. Consider n identical processing elements. All these are n identical processing elements that implements the logic function. Okay, so consider n identical processing elements, each implementing the logic function f input in parallel, right? So in the previous one, all the registers are connected in series or pipeline mode, but here all the register arrays will be connected in parallel, including with the logic functions. Okay, so that is what here. Assume that the consecutive input vectors arrive at the same rate as the single stage case examined earlier. Okay, so in the single stage case, first when the first clock arrives, the first input will be stored, or input is given to the register array. Similarly here we have the registers, many registers. Here we have n registers. All the n registers are connected in parallel, and the each input that will be inserted or that will be given to each array or the register array at a same clock pulse or at a same clock. Okay, if the first clock one is arrived, at the same time the input will be applied into the all the registers. Okay, so that is what here parallel processing or parallel processing approach. Okay, so the same construction you can observe here. This is the array. We have register array 1, register array 2, and register array n. Okay, but at each point, at each register, the input will be applied at the same clock pulse. Okay, that is called as parallelism here, right? So the input vectors are routed to all the registers of the n processing blocks. Okay, so if you give at a clock pulse 1, so if you give the input 1 to this register, at the same time all the registers will be loaded with the input vectors, and the output of those registers is given to the logic functions at a time. Okay, that is what here the input vectors are routed to routed means connected here to all the registers of the n processing blocks. Okay, all the registers of the n processing blocks. That means the output of each array register array is given to the logic function. Okay, that is nothing but functional blocks, right? So the output of functional blocks is given to the mux multiplexer, and it will give one by one the output, right? So here the input vectors are routed to all the registers of the n processing blocks, right? So gated clock signals, each with a clock period of n t clock, are used to load the each register every n clock cycles. Okay, gated clock signals, each with a clock period of n t clock, right? So here if you observe this one, it is nothing but f clock by n, right? So what is this one? Clock is divided with n, and that means for each clock. So here gated clock signals, each with a clock period of n times the t clock. The f clock, 1 by f clock is nothing but the t clock, are used to load each register for every n clock cycles. Okay, for every n clock cycles. So here we will what we call, we will insert the inputs into the array of registers, right? So next, this means that the clock signals to each input registers are skewed by t clock, such that each one of the n consecutive input vectors is loaded into a different input registers. Okay, so here at the time of t clock, each n consecutive input vectors is loaded into the different input registers. Okay, so this is the block diagram what we have for the parallel processing approach. Now each input register is clocked at a lower frequency of f clock by n. Total clock frequency is f clock, and it is divided with n, so it is very low frequency. Each input register is clocked at a low frequency of f clock by n. The time allowed to compute the function for each input vector is increased by a factor of n, right? So this implies that the power supply voltage can be reduced until the critical path delay equal to the new clock period. So how we can reduce here the power supply means, here by taking that the critical path delay equal to the new clock period, that is nothing but nt clock, right? So this implies that the power supply voltage can be reduced until the critical path delay equals to the new clock period of nt clock. Okay, so the outputs of the n processing blocks are multiplexed. That means here the outputs of each logic function is given to this multiplexer. Okay, so that multiplexed output and sent to an output register which operates at a clock frequency of f clock. Okay, so the output of the n processing blocks are multiplexed and sent to an output register which operates at a clock frequency of f clock, ensuring that the same data throughput rate as before, right? So the output of this, all the functional blocks are given to the what the multiplexer, and multiplexer will provide the corresponding output to the output register. Okay, the total dynamic power dissipation of the parallel structure, neglecting the dissipation of the multiplexer, is found as the sum of the power dissipated by the input registers and the logic block operating at clock frequency f clock by n, and the output register operating at a clock frequency of f clock, right? So what is the total dynamic power dissipation at this is nothing but the total dynamic power is nothing but what we call, that is per parallel processing approach, is nothing but it is the addition of the input register array and at the same time the functional block power dissipation and the output register power dissipation. So if you combine all these three, that is nothing but the input power dissipation, that is input register array power dissipation, functional block power dissipation, and at the same time output register power dissipation. If you add all those things, you will get the total dynamic power consumption in this parallel connection. Okay, P parallel, that is the dynamic power consumption that is equal to n C total multiplied with VDD nu square f clock by n. So here it is n means what is the n means here is nothing but we have n number of functional blocks. Okay, so functional block are n number of total single stages are connected in parallel, right? N number of single stages are connected in parallel, and each single stage will provide the C total VDD nu square F clock by N power dissipation. So that is nothing but for one single stage, what we have considered in the previous discussion, that is nothing but C total VDD nu square F clock by N. Okay, but we require for N stages that are connected in parallel connection. So that is nothing but NC total VDD nu square F clock by N plus that is nothing but C register, each input register and output registers we have. So that is nothing but C registered VDD nu square F clock. If you simplify this one here, N and N will cancel. Okay. So here, if you simplify this one, that is N and N will cancel. One second. So here the total dynamic power consumption that is in parallel processing approach is nothing but P parallel is equal to N into C total VDD nu square F clock by N. So what is this one? So this term in first we will consider this one. Okay. So this is nothing but the power dissipation for each single stage. So what we consider in the previous discussion. So that is nothing but C total. The C total is nothing but the input register capacitance, functional block capacitance, and output register array capacitance. Totally, we will consider as C total. That means here this term will indicate the power dissipation of a single stage. Okay, and if we have n number of these stages, that's why that are connected in parallel, that's why this is multiplied the total to calculate the total power dissipation due to these functional blocks. So what we will represent here is we will multiply n with we will multiply this single stage power dissipation with n, so that we will get n stages dynamic power consumption. Okay, so this is n stages dynamic power consumption, and here we have that I already told that the power dissipation due to three components, due to registers and functional blocks, and we have calculated the functional block. Here we are going to calculate the register capacitance and VDD nu square F clock. Okay, so this is what we have the complete equation. If you see this one, this n and n will cancel. If I consider the C total and VDD nu square and F clock is common. So what we will get here, if you take the common, C total means 1, it will be there, plus C register by C total multiply with C total VDD nu square F clock. This is the equation of the dynamic power consumption in parallel line or parallel processing approach. Okay, so now if you consider this single stage power dissipation and at the same time parallel processing approach, if you divide those power dissipations, what you will get, the amount of power reduction achieved in a n block parallel implementation is P parallel, that is dynamic power consumption in parallel approach by the single stage. So it is nothing but VDD nu square, and it is F clock into C total by VDD square. Okay, so if you simplify this one here, if you simplify by dividing that parallel line approach or parallel processing approach with the single stage reference power dissipation, you will get the equation as VDD nu square by VDD square 1 plus C register by C total. So this is the ratio of the parallel processing approach power dissipation to the reference single stage approach. Okay, so this is about the parallel processing approach, right? Next, the lower bound of switching power reduction realizable with architecture driven voltage scaling is found, assuming zero threshold voltage. The lower bound of switching power reduction realizable with architecture driven voltage scaling is found, assuming zero threshold voltage as P parallel by P reference is greater than or is equal to 1 by n square. Okay, so here if you considered if you avoid these things, that is what we call the lower bound of switching power direction realizable with the architecture driven voltage scaling is found. That means if you do the voltage scaling assuming zero threshold voltage, we will get the parallel approach to the difference power dissipation is greater than or is equal to 1 by n square. It is the ratio of parallel power dissipation to the reference or single stage structure power dissipation is greater than or equal to the 1 by n square. Okay, so two obvious consequences of this approach are the increased area and the increased latency. So what we have considered in pipeline approach, although the limitation is the latency will be n. Similarly, here it will not avoided, but the speed will be increased. Okay, so the delay will be reduced or the speed will be increased. So here two obvious consequences of these approaches or parallel processing approach is the increased area and the increased latency. Okay, increased area and at the same time increased latency. A total of n identical processing blocks must be used to slow down the operation speed by a factor of n. Okay, a total of n identical processing blocks must be used to slow down the operation speed by a factor of n. In fact, the silicon area will grow even faster than the number of processors because of the signal routing and the overhead circuit. Okay, in fact, the silicon area will grow even faster than the number of processors because of the signal routing and the overhead circuit, right? So here the silicon occupied area will be increases or silicon area will be increased due to this parallel processing approach. Okay, so here if you observe, this is the timing diagram what we have, right? So the timing diagram shows that the parallel implementation has a latency of n clock cycles as in the n stage pipeline implementation. So whatever we have considered in our pipeline approach, the same difficulty or the disadvantage is present here. It will also offers the latency of n clock cycles. Okay, so that is the disadvantage what we have. The timing diagram in figure shows that the parallel implementation has a latency of n clock cycles as in the n stage pipeline implementation. Okay, so if you observe here, this is the clock, actual clock here what we have. So the first clock will be obtained here from this point to this point. The first clock is from this point to this point. Okay, so the input one will be loaded into the all the register arrays at the clock one itself. Okay, so this is the clock one, this is the clock one, and this is the clock n. So at this point in this clock itself, all the input ones will be obtained. All the input ones will be obtained. And next, for the next clock cycle, so the input 2 will be loaded into the registers, and so on. After nth clock, only the input n will be loaded. That means to load all the n inputs, we require n clock cycles, because each clock cycle is for each clock cycle, one input will be loaded, second input will be loaded for second clock cycle, and third input will be loaded for the third clock cycle. Like that, for to load the n inputs, we require n number of clock cycles. So after completion of all the input loading, so the output 1 will be obtained for the corresponding input 1. Okay, so the same thing here we have represented. So input 1 is presented at the clock 1. Okay, input 1 is loaded into the registers. All the parallel registers are loaded into the registers by input 1, and that input 2 is loaded at the second clock cycle. Similarly, input n is loaded into the nth clock cycle. But after completion of loading of all these inputs only, we will get the output 1. Okay, that means how much time it is taking? N clock cycles we are getting, that circuit is taking to get the output of the input 1. Okay, so the output corresponding to the input 1 we are getting after n clock cycles. So that is the latency what we are getting in this parallel processing approach also. Okay, we already seen that in the pipeline approach, we are getting that n clock cycle latency. Similarly, here also we are getting the same problem, right? So that is what you can see by using this diagram. Simplified timing diagram of the n block parallel structures as shown in figure. So this is the uh, approach, that is parallel processing approach timing diagram what we have, and it is representing that uh, the first point is the first input will be loaded into the registers at the first clock cycle, and second input will be loaded into the registers by second clock cycle. Like that, n clock cycles is required to load n inputs. After completion of those n inputs, we will get the will get what the output of the first input one, right, or the output of the first input. So that is the process that is taking place in this parallel processing approach also. So this is also called as hardware replication. Why it is called hardware replication, right? So why it is called hardware replication means, if you observe this, so this single stage is repeating here. We are replacing the single stage at each point, like this and like this. Okay, so here we are not designing a new circuit or new functional block. So this hardware replication, the name itself, it is there in this process, is nothing but we are replicating the hardware again and again up to required number, right? So that means what here, it is hardware replication is nothing but here this functional block, the same functional block is repeated here, and this is repeated here, like that. If you want to construct an n stages of parallel processing approach, so we have to connect, we have to replicate the same hardware that are used for single stage. We have to replicate again and again up to you reach the n stages and parallel stages. So that's why it is called as what, hardware replication method, right? So that is what why it is called as hardware replication process or approach, right? So here we have the timing diagram in figure shows that the parallel implementation has a latency of n clock cycles as in the n stage pipeline implementation. Considering its smaller area overhead, however, the pipeline approach effect offers a more efficient alternative for reducing the power dissipation while maintaining the throughput, right? So this is what at the time of introduction also I told that wherever we are not we are not able to use this pipeline approach, at that point we are going with the parallel processing approach. Otherwise, we will go with the pipeline approach only, right? So consider here we will see that considering its smaller area overhead, however, the pipeline approach offers a more efficient alternative for reducing the power dissipation while maintaining the throughput. Even though here, if you neglect or if you don't consider the area occupied by this pipeline approach, so that is an efficient method to reduce the power dissipation. Okay, so that's why as compared with parallel processing approach, so we will go with the pipeline approach, but we have to consider one thing is nothing but we have to neglect the area. We have not considering that area, increasing area or the silicon area in the pipeline approach. Okay, so this is about the parallel processing approach and at the same time the pipeline approaches. Okay, for the low power design or the power dispatch to reduce the switching power dynamic power reduction. Okay, so this is about parallel processing approach. So in the next class, we will go with the estimation and optimization of switching activity. Okay, so what is switching activity? We have seen in the previous discussion while studying about the switching power dissipation. Okay, so here in this topic, we are going to study about what are the switching activities that is taking place and how we can reduce and all those things we are going to study in the next class. Okay, thank you for watching. Subscribe our channel.